Hola a todos, bienvenidos a nuestro tiempo juntos. Welcome to our time together. In this video, we're going to follow up with the work that we did last time. Specifically, we're going to build another circuit example. This is going to be called example 3. In our videos, I'm going to do examples that are enumerated odd. So I'll do examples 1, 3, 5, 7, so that you all can do 2, 4, 6, 8. Who do we appreciate? Practice without teaching. The example that you see in front of you has 3 components. It has a single current source and 2 1K resistors. The breadboard or wiring diagram that you see on the left of your screen corresponds to the schematic that you see on your right of the screen. We'll talk about those specifically in just a bit. Let's get started with our build. Notice that in order to build this circuit, we're going to need a single breadboard, which we see on screen. We're also going to need 2 jumper wires. In our case, our electronic learning laboratory kit comes with a selection of jumper wires. Here we want the orange ones. So we're going to go ahead and pick out 2. This is where the little set of pliers that I carry around in my kit come in helpful. I will note that there is a very good resource that I provide for folks that are wondering about the jumper wires. These jumper wires are well done. The coloring code actually corresponds with the same coloring code that is used in resistors. So in particular, these jumper wires that you see on screen here come in kits that have different colors. So you see that there are just metallic ones with no insulation: red, orange, yellow, green, blue, purple, gray, white, brown, and then there's a selection of red and orange and also yellow and green. Those colors follow the actual encoding that happens in resistors. So in particular, we see that no insulation is 0.1 inch, red is 0.2 inch, orange is 0.3. And the really fun thing about this is these are created in such a way that they align with the sizes of the breadboard. So in particular, if I put a 0.3 inch jumper cable in between, that allows me to connect 1, 2, 3. So there's 2 gaps in between, and it goes in the first and fourth hole. The same thing's true if I were to grab like a red one. That's 1 down, so red is 1 below, as we see in this little map here. So orange is 0.3, red is 0.2. When I were to go to put in the red one, this would allow me to connect not consecutive, but every third. So in particular, you see that I can get 1, skip a hole, 2. If I had no insulation, it would allow me to go this way. And that's a really, really nice thing about these jumper wires. They are color-coded in such a way that allows me to correspond my work really, really closely to what's happening in the actual breadboard. Let's go back to this circuit build. We have a half-size breadboard. We have 2 jumper wires. We need 2 resistors. So it looks like I already have some spare resistors lying around. And the last thing we need is a DC current source, which we've got here. I will note that in our wiring diagram, if you see up in this point, the color of the positive lead is red. When we actually created these, the students that made these, we decided to do white so that it was really, really clear which one is a current source and which one is a voltage source. The diagram on this actually also is a secondary specification. When you see the actual DC current sources, just realize that the white lead is the positive lead and the current runs from white down through black. So in the diagram, those will be red, but the actual physical circuits will be white on those leads. Okay, so I think we have everything that we need other than the actual battery. We'll do that in just a second. Let's go ahead and build this circuit. First thing we do is we disconnect the battery. That's already done for us. Next thing we do is we insert the jumper cable from E1 to F1. So here we go. That gap in between is exactly 0.3 inches, which is why the orange one comes in really handy. Sometimes when I'm struggling to do this, I actually might use my little tweezers to get those in there and then just push down. I shout out to Misha and Derek. We made these, some of my students and I made these together, and they said always put the jumper wires in first. So that's kind of exciting. So here we go. We're going to go ahead and put the next jumper wire across, what does it look like? E20 and F20. So I go down to the 20, E20 down there, F20 right there. I push all the way in. Next thing I'm going to do is I'm going to take my resistor and go from I1 to I10. So I1 all the way down to I10. And the last non-power source, so the last non-DC source, I'm going to take my second resistor and go from J10 to J20. And that should get me the right-hand side of my board. On the left-hand side of the board, I'm going to take the white lead and put it in A1. So here I put the white lead of my first current source and put it in A1, and the black lead and put it in A20. Now, let's go ahead and just analyze this quickly. Notice that all the contact points in the first row are connected. When I have this little jumper, that connects the first 5 to the second 5. So that jumper actually extends the conductor all the way down here. And we notice that there is a single wire that goes all the way down into A1. That's connected via contact points to this jumper. That jumper is a straight conductor that connects it to the other set. And then all the way up here. So when we look at our schematic, notice that at the top of my current source, I literally have one piece of wire that goes all the way to the first resistor. And that's exactly what's happening here. One piece of wire that goes all the way to the top of the first resistor. Then we've got our resistor, another piece of wire. So this wire comes out of the resistor, this lead goes under the contact points through this part, and that's a second piece of wire. So that thing right here is a second piece of wire. And then the third piece of wire comes down this way through the jumper and to the black. Notice that the actual layout of my circuit is not the same as I've laid it out in the schematic, because these wires are assumed to be malleable. We can stretch them and compress them. We can deform them. The wires themselves don't change the electrical behavior. Now, this does change when I'm thinking about power transmission lines. If these wires were miles long, we would have to think about that. But for the small actual physical distances that we're working with in these circuits, we can be a little bit flexible in how we actually implement that design on our breadboard. Next thing we're going to do is measure the circuit variables using a multimeter. Remember, each element gives rise to 2 circuit variables. So in this case, we have 1, 2, 3 circuit elements times 2 variables per element. That's a total of 6 measurements that we're going to make on this circuit. Let's go ahead and grab our multimeter and start measuring. All right, we're all set up. We got our multimeter. We have our battery ready. We are going to measure each of the circuit variables. Before we do that, though, remember that each circuit variable, when we take the measurement, we have to choose polarity. What we're going to do is we're going to actually label our chosen polarity prior to making our measurement, so that we know when we capture the data which red and black leads were connected where. Let's start with the current variable. We know that there are going to be 2 actual values that we're going to collect for our current variable. We're going to look for the voltage across the first current. We said that every time we're doing voltage, the current direction actually will define uniquely the voltage. We will always say that our reference goes from positive to negative. And the reason that we said that this was positive and that negative, we're going to assume the rule that when we're using a current source, the reference direction for the current is in the same direction as the actual source. That's analogous to the work that we did in voltage drops. So this is going to be the current running through current source 1. The corresponding voltage across current source 1 is going to be VI1. And remember, when we draw the current direction, that actually defines the positive and negatives, and vice versa. We're going to have, similarly, a voltage drop across resistor 1. In this case, a priori, we actually don't know which direction the current is going to go. For you electrical engineers, of course, you're going to say, yes, we do. I'm not worried about that. We can just assign these arbitrarily. This comes in helpful much later. If we say that that's the positive reference and that's the negative reference, we immediately know that our current direction, reference direction for this resistor, is going to go in that direction, and we'll call that IR1. Similarly, when we're looking at resistor 2, we can say that there is a voltage drop across resistor 2, why don't we just for giggles say that the reference direction for this voltage is opposite of the one before? As we get more sophisticated in our ability to understand what's going on electronically, we might change our attitude there, but I want to show that it is actually arbitrary. Anytime we choose a positive and the negative, the current goes from positive to negative, and that current variable we're going to call the current running through resistor 2. So with these reference directions, we've actually determined completely how we're going to set this up. Let's take each individual measurement and then capture our data on a data sheet. Here we go. We'll start with volts. Let's see. So the red portion of my voltmeter is going to go on the top of the resistor 1. The black is going to go on the bottom. And we see that it looks like a negative 2.471. So the voltage drop across this is a negative 2.471 volts. We're going to go ahead and just do all the voltage measurements at once. So in this situation, we're going to look like red on the bottom of resistor 2, black on the top of resistor 2. Whoa, that's really interesting. It says that it is a positive 2.472 volts. And then the next question is, what is the current, the voltage across the current source? And for this one, notice that we said that the positive was on top and negative was on bottom. And to do this, I actually need to connect my voltage to a wire. But remember, this wire right up here is actually electrically connected to the white wire, which I want to capture. So too is this wire down here. We notice that the corresponding voltage drop from the white to the red, from the white to the black using this polarity is negative 4.93. So this is going to be negative 4.93 volts. This is not a coincidence. Do you notice that if I were to sum these two things, it looks like that? We're going to call that Korsakov's voltage law in later videos. There's some polarity, there's some sign stuff going on, but this is a really interesting observation that there's some kind of linearity between these variables. Now that we've captured our voltage values with respect to these voltage polarities that we've defined prior to doing this, let's go ahead and now do our current values. So the first current that we're going to look at is the current running through resistor 1. We're going to go ahead and connect the red lead up top and the black lead on the bottom, since I want to go in that direction. And it looks like this is going to be negative 2.56 milliamps. Remember, each measurement has a sign, a magnitude, and units. So we're capturing all pieces there. Let's go ahead and disconnect these. We will reconnect this in the proper place, and in this case what we're going to do is, looks like we need this polarity, so we're going to disconnect the current source, and then we'll make the connection here. So the current is going to run through this thing, down through the red, through my multimeter, up through the resistor, and my multimeter is measuring positive 2.56 milliamps. And some of you might not recognize that, hey, it looks like you're actually measuring the current through the current source, and that's exactly correct. Kirchhoff's current law, which is another thing that we'll explore later, says that those are actually identical. Let me just go ahead and confirm. If I take the black here and the red there, indeed I get the same current measurement. So in particular, we just saw that the current running through this resistor is 2.56 milliamps. The current running through the current source was positive 2.56 milliamps, and in fact we can just confirm this one more time. So let's go ahead and disconnect this. We'll reconnect the top here, and then what we'll do is, remember, if we wanted to know how much current is running through, I could actually connect this up top. So we'll connect the black lead here and the red lead there, and now the current is going to run through the ammeter through this current all the way down. And indeed, look, it's the same measurement as we had previously. We have now filled out all the voltage and current measurements, the 6 of them. Let's make some specific observations about what we see. Notice that the current is going to go around in a loop. We're going to actually formally define loops later, but literally there's a flow of current. So you can think about them as electrons moving along this direction. So like electrons are actually moving opposite, but current, like there's actually a physical flow of something in this direction. And because it's a closed loop, because nothing is escaping here, the current running through this element is actually going to be identical to the current running through this element. Just think about it like water. If water was running here, all the water would continue along this way. Notice that is why we see that the 2.56 milliamps provided here is identical to the 2.56 milliamps provided there. And in magnitude, it's also identical to this measure, except this one is opposite. The reason that it's opposite is our reference direction for that measurement is in the opposite direction. Next thing I want to kind of observe, look at the mathematical model. So in our mathematical model, we said that there were going to be 2.5 milliamps running through. That is different than the actual physical dynamics. Now they're not different. It's 6/600ths of a milliamp is the difference, but it is not identical. And this is, again, one of the themes that comes up over and over and over again in applied mathematics. The model that we propose differs from the actual realization. And the question is, can we do something intelligent with that? The last thing that I wanted to note, check out how similar the current information is to the voltage information. It's not identical, right? And that's because Ohm's law says V equals IR. This scalar, if you divided 2.472 by 1,000, you would get something very close to that. Now, there is some imprecision in the actual resistance there, and that's why these numbers don't correspond completely. But as we get into Ohm's law, we're going to see there's a connection for the current running through the resistors and the voltage drop across the resistors. There's a connection there. That is Ohm's law. That connection is governed by something called Ohm's law. All of that is in play in this simple measurement process. In the next video, we'll continue with a different example, learning to build and then measure circuit variables. I'll see you in the next video.